Yeah, thanks very much also from me for giving me the opportunity to talk to you today here about our simulation. I'm Katrin Heitmann. I'm a staff member at Argonne in High Energy Physics Division as well as CS Division. I'm also a fellow at the CI and at the Carpenter Institute for Computation, Cosmological Physics at the University of Chicago. And as you pointed out, I will also talk about simulation with particles. My particles are much bigger. They're usually like 10 to the 9 suns heavy, so slightly different things we're talking about here. And but I will also talk about supercomputers. I will talk about simulation. So here you see one of the simulations that we are doing right now on Mira, and we are also connecting to real data to make sure that what we're getting is actually makes sense. Very quickly, collaborators. I have to thank a lot of people without whom I wouldn't be able to do this talk. And just to give you a very brief introduction to cosmology. So what we are doing in cosmology is basically we are mapping the universe. So here what you see on the right are maps of the universe in different wavelengths. The one problem in cosmology is that we have compared to physics is that we can't do controlled experiments. In physics, I'm interested in a specific behavior of a system, and I can set up an experiment, I can redo the experiment, I can look at different systematics by doing the experiment differently. But in cosmology, we just have this one universe. So what we do is we observe the universe in different wavelengths. And so here you see examples. Here's the universe in the X-ray, in the cosmic microwave background, in the gamma ray, or in the optical. So here what you see is galaxies. And from these observations, we do statistics on these observations. We measure the correlations between the objects that we are measuring. And from that, we infer information about the content of the universe as well as its evolution. And so there is this inference step that we have to do in order to get from this map actually to the information that we want to get about the universe. And at this point, we use large simulations because the universe is a complicated system. So without simulations, it's very hard to get the information. And just to show you an example of the kind of observations that we are looking at, this is from the Slow Digital Sky Survey, which is a telescope in New Mexico, 2.5 meters, and they are mapping out the distribution of galaxies. And so what you see here is this purple shade is actually a sea of galaxies, and we are going to zoom in now. And unfortunately, the light here is a little bit not so good, so you can't see that much on the screen. But so what you see now is that all these little points are galaxies that we are measuring, and we are zooming in onto these two galaxies that are colliding. And basically, what I want to show you is this enormous dynamic range that we have in the data, that we really have a lot of information on which we can learn about the universe. And very quickly, cosmology on the slides. So we know that the universe is pretty dark. 95% of the universe is in so-called dark energy and dark matter. And dark energy has been discovered for the first time in 1998, and what it describes is basically that the expansion of the universe is accelerated. And if you would think about, if you wanted to have like a cartoonish example, if you throw a ball in the air, instead of it coming down, it accelerates straight up into the sky. That's kind of what dark energy is doing to our universe. And so we are trying to figure out what it is, what is the origin for this. Another interesting question is, why is it important now? If we would have lived a few billion years earlier in the universe, we would not exist this. So these are the kind of questions that we are trying to answer with observations. And then there is the dark matter. So we have observations that 27% of the matter in the universe is dark, and which means it doesn't emit or absorb light. And we have indirect evidence for this, but we also want to directly tap the dark matter particles. The other piece of knowledge of cosmology that we have is how did the universe evolve and how did structures form. And so here you see a cartoon, unfortunately also this comes of a little basically here we have the Big Bang, which starts at some point. This is where the simulations actually start, that I will show you in a few minutes. So they start when the universe was roughly 50 billion years old. And so it starts from initial conditions which are determined by primordial fluctuations. So we have small fluctuations on a relatively on a Gaussian field. And what gravity does then to these small fluctuations, it pulls them together and structures start forming. Within these structures, the galaxies are forming, and you get into this nonlinear distribution of structure formation. And down here would be today where you can see the distribution of galaxies. And you might have seen on Monday that there was a lot of excitement in the cosmology community, a lot of news article about primordial gravitational waves. And this kind of science actually was hit here into the initial conditions of the universe. And so it was in the New York Times. It was also in my favorite German newspaper, so this says signals from the birth of the universe. This is actually the telescope that made this discovery. So, so this was very, very exciting news. If this holds, everybody in the community thinks it's a Nobel Prize. This is the Nobel Prize discovery. So this is really, really great. So I can populate this dark matter distribution with galaxies, and then we can measure the distribution, like the two-point correlation function, which is shown here, and compare it to the real data. What you see here is these black points with the error bars are actually from the Sloan telescope, the measurements. This red guy here, the dashed line, is when you just take the dark matter distribution and calculate the two-point correlation function. And the blue line is if I actually populate the galaxies into my simulations. And what you can see from this plot is actually that the observations and the simulations agree really beautifully. And what we want to do in the future is make these error bars smaller and smaller on the observational side, and then get better and better handles on the underlying physics of the universe. So how do we do the simulations? So here is on one slide what we are doing. We are solving, basically gravity is the dominant force that we are looking at, and we have to solve the Laplace of Poisson equation for this. It's a six-dimensional equation, which you can see here, and computationally this is very, very hard to do, basically impossible. So what people do in the field is they use n-body simulations to basically tackle this problem. So what you do is you replace distribution functions with trivial particles, and if you do that, what you can see is that actually this problem becomes an n-squared problem if you do it in a naive way. So then people thought n-squared is still not good enough, so they came up with different ways of solving these equations with tree methods and with grid methods, and you can get this down to n log n algorithms. So each of our particles in the simulation is of the order of 10 to the 9 solar masses. In order to simulate a large chunk of the universe, and you roughly need billions to like a trillion particle to get this to get the whole universe in there. And what you can see here is how this time evolution looks like when you do this. So you start off with this smooth Gaussian initial field, which has these perturbations that we get from theory. So you can see that there's light yellow regions in here. Then you start the simulation, gravity starts acting. These regions become clumpier and clumpier over time, and then you see here the final distribution of the dark matter in the universe. And I always like to show this quote from Bob Dickey from 1969, where he said the universe is far too complicated. A structure can be studied deductively, starting from initial conditions and solving the equations of motions. But this is exactly what we're doing today. So the supercomputers really help us getting there. This again doesn't show up because of the light very well, but this is simulation that we're actually running right now on Titan. It runs on almost 90% of the machine. It involves 500 billion particles, and what you should see in principle is again the structure formation. So you can make out a little bit that here these structures form, how the particles clump together to form these dark matter halos. And so amazing thing about the simulation is that I'm only showing you the output from one node, and we are running on 16,000 nodes. So we have 16,000 times as much information as you actually see in this video.
When you say it's currently running, how much through the whole run do you?
Roughly half.
Okay.
We started like a month ago. But it's obviously not constantly running. So for the rest of this talk, I now want to focus on our simulation code, which is called HAC, or Hardware Hybrid Accelerated Cosmology code. And I want to give you a little bit of a story about HAC, how it started and where we are at right now. And it all started with an email from Andy White when our group was at Los Alamos, and Andy White was the head of computing at that time at Los Alamos. And he asked this question: what if you had a petaflop? And basically he was alluding to Roadrunner, which became the first machine to break the petaflop barrier. And he had this really nice idea for the basic scientists at Los Alamos to make this machine open for basic science for 6 months. So this is Los Alamos is a weapons lab, and these very big machines usually immediately go behind the fence, so nobody can touch them. It's not doing weapons physics. But he thought that this was such a great opportunity that everybody should have a shot to work on this machine, and for 6 months you can just do science on it. And the way how Roadrunner achieved this petaflop performance was via cell acceleration. So it's quite similar to the GPU, it's just a different accelerator that you use. So you have your conventional cluster, and then you have the cells attached to them, and they give you the performance that really makes this machine so interesting. The problem was that at that point in 2007, 2008, when the machine came, this architecture was thought of being crazy, and Andy White would have said it's actually forward-looking. And it either required major code rewriting, design, or in our case, we actually ended up writing a totally new code for this machine. The one problem that we saw immediately, obviously, was that Roadrunner was a one-of-a-kind machine. You don't know any other cell accelerated machine anymore right now. And so we didn't want to write a code to just run it for 6 months and then throw the code away. So we had to make sure that if we write a new code, it had to be portable. Cosmologists are poor, so this opportunity to run on a large machine like that was really great for us. So we said, okay, we go and design this new code. And the outcome was MC3, which stands for Mesh-Based Cosmology Code on the Cell, and which later became HAC. So again, my favorite newspaper. It was actually, it's always nice because I can send my mother an email saying, look at this newspaper, and she can read it, right? And something about us is in there. Another thing which I find funny is that we Germans always like to give gender to things. So actually, Roadrunner is he. He is the fastest calculator in the world. And they were very excited about it. They said technology of the future leads by example. Here, Cosmology was also in this article, so it was actually kind of exciting. And so we started thinking. So this is us, the people who have to write the code for the machine, and these are the computer scientists who don't want to hear that this might be actually not an easy thing. They're talking about exascale, hybrid machines, GPU cells, multi-core, you name it, right? But they don't really tell you, like, how do you make use of these machines in an easy and good way. So just a little bit about the architecture of Roadrunner, and everywhere where I say the cell, you can say GPU size. The one small difference that the cell actually has a lot of memory. So basically, the design of the system was the following. So you have this Optimum computer, which has only 5% of the total compute, but it has half the amount of the memory. And for people who deal with particle simulations, memory is important. So the more particles we can stuff into our simulation, the happier we are. So we want a lot of memory. So we cannot just say, well, we don't care about this optimum level because a lot of memory is sitting there. So that was one thing that we had to keep in mind. Right, so this is our optimum level, it's the blue stuff. And then we have the cells. So the cells are here, these pink guys. So the cells have, as you can see, 200 G-flop per cell they have to compute. The big problem that you see also immediately is, and this is the same for the GPUs, is that the cells, when they talk to each other, they have to talk through the CPUs. So if you do a calculation up here, and you need to talk to these guys about what you just have done, so if your calculations are not independent, you have to go through the CPUs, and this is actually very slow. So even if you do a lot of calculations on the cells, it doesn't help you if you afterwards have to send your information down back to the CPUs and back up here and have these guys talk to each other. Finally, the multi-layer programming model makes things complicated. So the cells had to be programmed in cell intrinsics, so a language nobody knew that much about. I mean, it's C-like, of course, right? It's not totally crazy. But still, it's a language which is very specific to this architecture. So basically, the question was for us: one, can we come up with a code design that allows us to use all the memory here and there? Two, can we come up with something where we are not bottlenecked by this communication that is slow through the CPUs? And three, can we come up with something where we can throw out the cell code later on and replace it by something else, like for the GPUs, we have OpenCL modules, so that we haven't wasted too much time. And fourth, the algorithm that we use here on the cell should be pretty easy, because the poor person who has to program that doesn't understand like month and month programming in a new language, and so we didn't want to make this too complicated. And this is basically, in a nutshell, what we came up with. So Hack has two major components which take all of this into account. So the first component is that we are splitting the force calculation that we have to do into a long-range part and into a short-range part. And so the long-range part, which we are doing in this case, which is an FFT-based solver, it's a uniform grid solver. So this part lives actually on, in the Roadrunner case, on the CPU part of the machine. And this part is unchanged for each and every architecture that we use. So basically, we wrote this, it's MPI based, and it also dominates the performance of our code in the sense of it's a code with scale. So if we are really good in writing this very nicely, you only have to write it once, it will work on each and every machine. And we put in a lot of work here. So the second part is the short range part. So what happens is that the long range part, if you work with these codes, like uniform grids don't give you much resolution. You want very high resolution on very short scales. So here what we did was we came up with, so you can do this with different algorithms on the short ranges. You can use tree algorithms, or you can do direct particle-particle interactions. The tree algorithms are nice, but, and I can talk about this after, probably a little bit more, what we have done here. But the problem is that they have relatively complicated data structures. So they have to think a little bit about. So on the GPU or on the cell, for example, where you have a lot of compute, you want something simple. You want something like the direct AND-squared method. But on a machine like the BGQ, for example, they don't have that much compute, but data structures are not that much of a problem. You want something faster like the tree. So basically, we said we can have these different algorithms depending on the computing architectures we are on, and we can swap them in. So, and that you can see here, kind of cartoonish. So the very large scales, we have the particle mesh part, which is independent of architecture. And then on the very small scales, you can exchange trees with this particle-particle methods and really optimize them for the architecture you want. The second part that's really important is the overload concept. So I told you that it's difficult that you don't want the cells or the GPUs have to talk to each other all the time. So one thing that we did was we implemented the following. So here you see, again, a cartoonish view of the ranks on your computer. So each of these big black guys in the rank. And the green particles are what we call the active particles that live on this rank. And now you have to talk to your, so they interact obviously with the particles living on the neighboring bands here. But you don't want to have this communication going on at every time step. So what we said is we just tell them about the active particles on the neighboring ranks, so these are the red guys, which we call passive particles, so that the force calculation on these green guys take into account what these red guys are doing. And since in cosmology the one nice thing is that particles don't move very much, we can do this. So these red guys will move according to the right force laws, every time step a little bit, and then every 10 big time steps or something like that, you just refresh this. You just say, okay, now I'm going back, I rebuild this overload concept and make sure that the red guy still has the right forces. So these were the two major things that we did. And now you can see the other nice thing is that the short range solver, which really lives in here, can be optimized in a serial way. So all the parallelism is living here in the long range groups. So that's very nice. So that makes it easy to swap in and out groups. And here you just see very quickly, this was the first time that we ran on our Roadrunner. Here you see the improvement of the cell short range solver versus the optrons. That's almost a factor of 100. Here's the cell, here's the optron. Here you see some weak scaling plots for the whole code. So everything worked really, really nice. Then, as I said, the next thing was, and a little bit slow, was that we wanted to move the code to GPUs. So the one major difference here is that now you also have unbalanced memory. So the GPUs don't have as much memory as the cells have. So you have to start streaming your particles through the GPU. The other thing is that you have a new programming language. Now we used OpenCL, and later on we also actually just in Lukians from NVIDIA with a free version, which is a CUDA version of the code. So basically it shows that you can swap out the short range solver very easily, replace it with something that lives on the GPU, and things are working really well. So this was a Gordon Bell finalist paper last year, and here again you see a scaling plot, and we achieved peak performance of almost 21 petaflops on Titan, and this run that you just saw is basically running almost. For the BGQ, again, the idea is the same. Fortunately, the long-range solver worked really, really nicely. It scaled up to 1.5 million cores on Sequoia at Livermore, so it worked really, really well. So here again you see scaling plots. So this is the scaling plots, this time per seconds per particle. Number of cores goes up, and this is the performance. So the long-range solver didn't have to be changed much, and the short-range solver was replaced from an n-squared solver to a tree solver. And again, it worked really, really well on Sequoia. We achieved 14 petaflop of sustained performance, and this was one of the finalists actually in 2012. So overall, this concept works really nicely for us. And here's another simulation. So this is actually a simulation that's going on Mira right now. It has even more particles than Titan run. It has 1.1 trillion particles. But each of these particles is a little bit heavier than the Titan particles. So it's a different regime that we are actually looking at with these two simulations. But the code is running well. And just in the last couple of minutes, a few examples of what is the science that we are doing with the code. So here you can see, at the start I told you we now know roughly what the content of the universe is. And here I changed this a little bit. So this is what I told you about. This is the dark energy and dark matter model. Here I just took out the dark matter completely. And so you can see that the clustering of the matter is different. And this is how you can measure and simulate actually what's going on in the universe. Here I gave the dark matter component a specific property and made it a little bit more, so everything gets much more fuzzy. And so this is how you can do cosmology in these simulations compared to observations. And right now on Mira we are carrying out a campaign where we look at different dark energy models. We are exploring the lightest massive particle in the universe, the neutrino, and we see like what can these structure formation measurements tell us about the neutrinos. We are building high precision prediction tools from these simulations so that you can actually use them to analyze the surveys even more. Here's another very quick example. Again, unfortunately, the projector doesn't get this quite through. But these are Hubble Space Telescope images, and so you see here these arcs. strong lensing observation. And basically, you can see that in the simulation, you can reproduce this. You can simulate images that the HST will see, and then you can compare statistics, like how many arcs do I get in my simulation, and that can tell you then if your underlying model was actually correct compared with what you see. And this is yet another one. This was actually from the Roadrunner simulations that we did, where we map out more of the structure in the universe with high-resolution lasers that shine through the matter distribution to you. And so this measurement was done by now by the DOS survey, which is also part of this. So you can do a lot of things. And basically what we do is we do generate these dark matter simulations, and from there we can create different observational tools. And just to summarize, it's exciting times for cosmology. Everybody on Monday was really very excited. There's at the University of Chicago this afternoon, the cosmologists had like a session just the whole afternoon on the discovery of primordial gravitational waves. Analysis of current and future cosmology data requires large-scale precision simulations. Current and future supercomputers allow such simulations, but they are not that easy to use. And so with HACK, we try to address both challenges, really get these very large simulations up and running, and be sure that when Argonne gets the next supercomputer, we are still in business. And so HACK was designed having in mind that we want high performance, but still easy portability. So if the next mission comes, we are ready to go. It does run on all currently available supercomputing architectures. So we ran it on Edison, at University, we ran it on Blueprint systems, on Python. So it's really running well. In addition to the code itself, extensive work has been done on the analysis tools. Just the simulations alone is not all that you have to do. You have to also create really the observational data on top of that in the end, so that you can compare what's available in the looks like. And currently the largest cosmological simulations are on the way, and hopefully more extended science will come soon. Thanks.
Thank you. So, questions? Yeah.
If you can switch back to the slide where you were describing the cell architecture, something just occurred to me when I saw this. You're dealing with really big distances, right? Because it's a cosmological simulation. How do you deal with the fact that it's only single precision, internal numerical stuff?
Actually, our output is mixed precision. So we do double precision for the large scale, for the large read, for the PM solver, and single precision. So yeah, it's good.
How few particles can you actually assign to each of the CPU cores with this code until the scaling really breaks down? Because you had strong scaling where you're pushing it up, but it seems like you have millions of particles per core for the solar system, right? So it's really computer heavy. Do you know what the limits are in terms of how few you can actually assign to these cores before you really start getting good scaling?
Yes, so obviously our code, so the load balancing becomes worse and worse the further we push out in the evolution, right? At the start it's not a problem at all. If you go further down, it gets worse. And so the one difference between the Mira run and the run on Titan is that the numbers of particles per core in the Titan run is 10 times more out of balance than on the Mira run. But since the GPUs are so fast, it doesn't hurt us that much. And I can give you more numbers, but yeah, it's a problem, and we can't push right now to whatever we want.
But there's a
but
technical.
we are working on that.
There's a technical difference between the load balancing problem we have and load balancing.
Oh yeah, yeah.
Technical difference is that we have the same number of particles per node. They don't change very much. But the actual distributions have an enormous dynamic range. So what happens is that you can have a very tight clump of particles, and that will then dominate the local. So of course, in cosmology code, the first generation of cosmology code, load balancing was done by space filling curves, like you showed. But we are moving away from that because that ruins the communication patterns. So we keep much more near stable communication patterns. And we try to get rid of some of the overload load balancing problems one way or another. But the way we are going to do it And the next generation code is done load shaving. So I can talk to you more about that.
Yes, good. The other thing is tree versus the bushes. Right?
There's all kinds of other stuff that Katrin mentioned, chaining meshes,
Yeah, right.
bushes instead of trees, it's all that.
Yeah, so yeah, we at the very beginning, like, we did just the brute force, and then we pretty quickly realized, okay, we have to improve here.
It's a multi-scale code in the sense of all things.
Yeah.
So you keep scaling up, but is there do you have some idea of when computers will be fast enough and you won't need to scale anymore? Or will you always? I mean, does your simulations converge at some point on the cellular?
So what we would want, and what the computers are not giving us enough of is memory. So we want to stop doing particles in there. And if we get more particles, then it becomes more computer-intensive. So structures are just resolved by many particles.
We also want more speed. I mean, right now what's happening is that the cores are getting weaker. They're just giving us more of them, but we couldn't care less.
So my question was more, is there some number of particles at which you expect things to converge and you won't need more?
Oh, I see what you're saying. So that's like, I think, to be honest, that number is not too different from where we are. I mean, if you could run an order of magnitude or 2 more particles, that would be sufficient.
The one thing is that the physics will become much more complicated. So we have to go and put in the hydrodynamics.
It's the extra physics that you need to add at that point.
Because if you go to smaller and smaller scales, more and more physics becomes relevant besides that.
Yeah.
And then
Okay. Other questions? Well, thank you very much.